Welcome to Unit 9, Inference for Quantitative Data, Slopes. This is topic 9.5, carrying out a test for the slope of a regression model. In the previous topic, 9.4, we talked about setting up a test, covering steps 1 and 2. In this video, we are going to rehash those steps, but we're also going to really focus on steps 3 and steps 4 of the process for a test for a slope of a regression model. All right, so what's next after what we've already learned in the previous videos over setting up a test? Well, step 3 is finding the t-score in the p-value for your actual sample slope that you found in your data. And step 4 is to make a conclusion. So let's talk about step 3, finding the t-score. So the t-score represents how many standard errors our sample slope is from the mean of the sampling distribution. So basically we're identifying, hey, we have the sampling distribution that shows all possible sample slopes from a sample of size n, and we want to say, all right, where is our slope? The actual slope that we got in our data, where does that slope fit in? And that's what the t-score is going to do for us. So to find that actual t-score, it's quite simple. You're going to take the slope that you found, which is b, which again, multiple different ways to find b, but the easiest way in these types of problems is just with a computer output table. And then we're going to subtract what we call the null slope, right? Now remember, beta represents the slope that we believe to be true in our null hypothesis. So typically here, this is going to be given to you in a problem. You know, in the previous videos, I mentioned like 5, maybe somebody said the slope was 5, what have you. But if you are just trying to find out, like if the question is just saying, hey, is there a linear relationship? Does this data prove that there is a linear relationship between x and y? Well, in that scenario, usually the null slope is just 0, because the null would be no relationship whatsoever. And remember, a slope of 0 is no relationship. And the alternative is that we are saying, no, there really is a positive slope or maybe a negative slope greater than 0 or less than 0. So this value right here is again called the null slope, and that is what we use in the null hypothesis, which in a lot of cases, if you're just looking for a relationship, is 0. Otherwise, it's going to be in the problem. You're going to read the problem and it's going to tell you what the believed to be slope should be. All right, so the sample slope b, again, is going to be really given to us in that data analysis output. There are multiple different ways to find the slope b that we talked all the way back in Unit 2. You could do formulas by hand. You could have your calculator do it. But again, in these types of problems that I've seen on the AP test, you're going to be given those computer output tables, or what's called a regression analysis output, and the b value will be given there. Also, the standard error of the slope, remember, this number is also going to be given to you. In fact, in the table, it's directly next to the slope. So you don't have to do any really hard work, or you don't really need to know the formula for what that standard error of the sample slope is. All right, so the t-score itself is also in the regression analysis output. What? Yeah. So yes, I'm teaching you how to find the t-score. But believe it or not, you don't even have to do the work to find the t-score, because if you have one of those regression analysis outputs, the t-score is given to you. It's crazy. These problems are so awesome because they truly involve very little work. But it's actually really easy to do by hand as well. And I'm going to show you that in some examples. Now, the other thing you need in step 3 is the p-value. Now, remember, what is the p-value? It is the probability of getting the sample slope that we saw or more extreme, assuming that the null hypothesis is true. So it's super important that you understand what a p-value is, because a p-value is, you know, in a nutshell saying, hey, listen, how significant or insignificant is our sample slope? Is our sample slope really, really high, which shows that the null that's in the center is completely not right? Or maybe it's really, really, really low, which again would show that the null that we thought was in the center is not right. That's what we're trying to do here. So to get that p-value, we are going to use TCDF, just like we use. Remember, these are t-scores. We're using TCDF. So when you go into your calculator, and we're going to show this in a couple examples, and you enter in TCDF, you need the t-score. And if it's positive, you're going to go towards infinity. So you're going to look above it. If your t-score is positive, you're going to start at that t-score and go towards infinity. If your t-score is negative, then you're actually going to start down at negative infinity and go to your t-score. Because remember, the definition of a p-value, it's the probability, assuming the null is true, of your sample slope being found or more extreme. So if your sample slope is already on the positive side, then or more extreme would be even higher. If your sample slope is on the negative side, then or more extreme would be even lower. So it's really important that you understand. Oh, sorry. One more thing you're going to need is the degrees of freedom. And the degrees of freedom is your sample size minus 2. Remember, 2 variables, so sample size minus 2. So the interpretation is super important, but it's also important for me to note that in the actual 4 steps, you don't have to interpret the p-value. You have to make a conclusion in step 4 based on that p-value, but you don't have to explain what it represents. But you never know on an AP test if you will be asked as a side question to explain what that p-value is. So interpretation of the p-value of a significance test for the slope of regression should recognize that the p-value is computed by assuming the null hypothesis is true. It's super important that all p-values that we've discussed this entire year are all on the assumption the null hypothesis is true, meaning we are assuming that the true population slope is equal to the particular value stated in the null hypothesis. And that's the whole point, right, is that we build this sampling distribution on the assumption that that null is true. So we assume the null is true, and then we look for our sample statistic. Where is our sample statistic located? And that is the whole point of trying to determine, is this significant evidence? Is our sample statistic so high that we need to reject the null? Or is it so low that we need to reject the null? Or is it really just in the middle, kind of normal, just a little higher, a little lower, that we don't really have enough evidence to reject the null? And that's exactly where we make our conclusions, which is a perfect lead in to step 4. So we have seen these same conclusions over and over again the last couple units, but a formal conclusion explicitly compares the p-value to the significance level alpha. So make sure you please start off by comparing your p-value to the significance level. Now remember, there are a couple different levels of significance that we use, but the most famous ones we use are 1%, 0.01, or 5%, 0.05. You will see some people that maybe use 0.025, whatever. Okay, so if the p-value is below the level of significance, so whether you're 1%, 5%, if your p-value is lower than your level of significance, this is when we are saying that what we found, our sample statistic, is significant. So we will reject the null hypothesis and say that we do have significant evidence that the alternative hypothesis is true. Basically, our sample statistic was too far from the center for the center to still be normal or be true, which is why we have that evidence to reject that center and go with the alternative. So if the p-value is above the level of significance, this means that our sample statistic is actually quite likely to occur, assume the null is true. Here we fail to reject the null hypothesis and say that we do not have significant evidence that the alternative hypothesis is true. All right, so the results of a significance test for the slope of a regression model can serve as the statistical reasoning to support the answer to a research question about the sample. So that last sentence is really just basically saying, hey, if you make the right conclusion, if you do the work correctly, a significance test is capable of answering that research question of, hey, I wonder if there really is a linear relationship, if there really is a slope between these two variables. So we can do a test. I guess, a lot of kids kind of overlook that last sentence, but essentially it's really, really important. It's basically saying, hey, all this work you're doing is going to allow us to answer this super important question that we were posed with. All right, so let's look at our first example here. It's the same example we started in the last video as well. So we looked at the weights and gas mileage of 12 random cars to find the relationship between the two variables. So we got the weight of cars, that's our explanatory variable x. We got the gas mileage, that's the response variable. And, we first look at this scatter plot and I say, all right, well, based on these 12 cars, it looks pretty negative. It looks pretty linear. As the weight of a car goes up, the gas mileage goes down. Strong evidence as it appears, but all I'm doing is looking at a scatter plot, right? The point is, if I got another 12 cars, would I see the same thing? Who knows? Well, that's going to be kind of the point of a test, is allowing us to answer that question. So here's a couple other things that we talked about previously that we are going to need. Residual plot, histogram of the residual values, and that ever important computer output table. All right, so here the question is, does this data give significant evidence that there is a negative relationship between the weight of a car and its gas mileage? In our data, we don't need a test. In our data, yes, there is clearly a negative relationship. But the question is there a negative relationship amongst all cars? So that's where we're going to run a test at the 1% level to find out. All right, let's quickly review step 1. This is a t-test for the slope of the regression line between weight of a car and gas mileage of a car. Don't forget that context. There was no slope given to me, right, in the problem. They didn't say, hey, I think the slope is 5. Do you think it's more or less? No, they're just saying, is there evidence of a negative relationship? So the null would be that there's no relationship whatsoever, which is a slope of 0. So we're going to say that the true slope beta is 0. There's no relationship. Weight of a car goes up. Who cares? The gas mileage isn't affected whatsoever. And the alternative is that, no, there really is a slope that is less than 0. There really is a negative slope that shows that for all cars, as the weight goes up, the gas mileage goes down. All right, the conditions is what we need all that extra stuff for, all those charts and tables and stuff. But, you know, the one thing I have seen a lot of problems in the past with the AP tests is, since there are so many conditions here, I'm not trying to say to ignore them or don't learn them by any means. But a lot of times it will say that these conditions are met. Don't worry about checking them. But we still need to run through them. The scatter plot of weight versus gas mileage does show a strong linear relationship. I mean, if you don't have a linear relationship to begin with, I wouldn't even conduct the test. The sample of 12 cars is, of course, random to avoid bias. The sample of 12 cars is less than 10% of all cars to assume independence. The histogram of the residuals looks to be approximately normal with no major outliers or skewness. The residual plot also shows similar variability for each x value, which basically means that I don't see any residuals that are way off base flying all over the place. Yes, some are positive, some are negative, but there's similar variability between them all. All right, and then finally, I do need to identify that I'm going to build a sampling distribution assuming that there is no slope, assuming that the slope between these two variables is 0. So that's why I'm putting smack dab in the middle. I'm going to assume that the mean of all sample slopes is 0. Meaning that, you know, I get that some samples might even show a positive relationship. Some samples might show a negative relationship. But if you average all of those samples out, you're going to get 0 because I have to assume that there really is no relationship between the weight of a car and the gas mileage. And the standard error, of course, for that sampling distribution comes from the table. Remember, alphabetical order, first column A, that's the y-intercept, which we do not need for this problem. B, that's the slope, that's our sample slope. And then right next to that right here is the standard error, appropriately marked in the SE column for standard error. All right, now for the new stuff. Get that t-score. So remember, to get that t-score, we're going to take our sample slope, which was negative 0.00714, and we're going to subtract the null slope of 0. We're going to subtract the fact that, you know, we believe the null to be true, right? We're starting off with the assumption that the null is true, and that means that there is no relationship whatsoever, which is a slope of 0, and we're going to divide by that standard error. So essentially, we built the sampling distribution centered at 0, up 1, 2, 3 standard errors, down 1, 2, 3 standard errors, and we want to see, where does our sample fall? Our sample had a slope of negative 0.00714, which to the naked eye looks like it's only a little bit below 0. My goodness, negative 0.007. But based on the t-score that takes into account the standard error, this is actually very, very low. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.75. It's like way the heck over here somewhere. So this is a very, very low sample if the null is true and there is no relationship. So the t-score is negative 0.75. Now check this out. Remember, I talked about this a little bit ago. Look at this. Look at this. Right next to the standard error is another column called t-stat. That's the t-score. So yes, I took the moment there to calculate the t-score, but I didn't even have to. There it is. In fact, they even used more decimals. There's the t-score right there. I did not even have to actually calculate it. It's right there in front. That's the beauty of these tables, is everything you need is right there. All right. So basically, guys, this is an unbelievably low sample, right? But what's the probability of this sample happening? That's the p-value. So what's the probability that any other possible sample slope is less than, more extreme than mine? Now, why am I going less than? Because I'm really, really low. I'm really, really negative. I'm way to the left. So, or more extreme means even lower. So to answer that question, that's the probability that a t-score is lower than negative 12.75, which I'm going to use TCDF to calculate. Now, you could use all of the decimals that was given in the table, but I'm going to stick with the 2 decimals that I got from my actual calculations. I mean, you know, it's not going to be that far off of an answer. All right, so when I go and grab my TCDF here, second variable, second vars button, you'll see number 6 there is TCDF. And this time I want to look below, right? So I'm going to go from negative 99, that's acting like my negative infinity, since I don't have an infinity button, up to negative 12.75. And remember, I had 12 cars. That's 10 degrees of freedom. Sample size minus 2 here. And we get 8.24. But wait a minute. Check out this e to the negative 8. That means I got to move the decimal 8 times to the left, which actually produces 7 zeros. So that's 0.00000000824. Okay? So that is my p-value. All right, so we talked about this computer regression analysis output has everything you need. So let's take a look at it one more time. So in the column for the slope, which is the bottom column, remember alphabetical order, A, y-intercept on top, and then underneath that slope. So the first column, we have the actual slope of our sample, negative 0.00714. Then we have that standard error, which is super important, that we need for confidence intervals and for the test. And then we actually have the t-score. So we don't even have to actually calculate the t-score. It's right there in front of us, negative 12.75. And then check out what's next to that. The p-value. The p-value. Yes, that's the p. So we don't even have to find the p-value. But I have to make one super important observation here. The p-value that is given in these tables is a p-value for an alternative of not equal to. It's just how these tables are created. So remember, we were specifically looking for a negative relationship, right? So our null was that the true slope was 0, and the alternative was that the true slope is negative, less than 0. But, you know, this computer output, they don't know that you're looking for a negative relationship, or it doesn't necessarily know that you're looking for a positive relationship. Remember, this computer output table is just like calculated and given to you. You don't really do anything other than put the information into it, right? You don't like ask it the question and it knows what you're doing. All this, you know, your Excel could do this, Google Sheet could do this, your calculator could do this. This computer output table is simply created from nothing but the data. All you need are your X's, in our case, the weights, and all you need are the Y's, the gas mileage. And this can be done, right? This is just an advanced statistical software that could do all the math for you. But at the end of the day, it's making all these calculations based on only the data. So it doesn't know that you want to look below because you want to be negative, or you want to look above because you want to look positive. So it automatically creates that p-value on an alternative of not equal to 0. So if you remember, when you have an alternative that is not equal to 0, you have to double your p-value. So this p-value is doubled. So in our case, since we are looking for an alternative that's less than 0, we would need to take half of this p-value. Now, just to prove this to you, this is the p-value we got, right? This is the correct p-value for our problem because we were looking to be negative, which is less than. But if I double this, you know, if it was a two-sided test where the alternative was not equal to, notice I get the 1.64 e to the negative 7, which is exactly what is in the table. So, you know, it's really not that hard to get the p-value on your own using TCDF, but if you want to even shortcut this more and not do any calculations, you can use the p-value that is in the table. But remember, if your alternative is one-sided, you would have to cut it in half. So you would have to type that number into your calculator and cut it in half to get the p-value. But to be honest, guys, I mean, look at this work. I mean, is it that difficult to find the t-score and p-value on your own? It's probably good practice to do it anyway. All right, so let's make sure that we understand what this p-value represents. Assuming the null is true and that there is no linear relationship between car weight and gas mileage, the probability of seeing a slope of negative 0.00714 or lower or even more extreme is 0.000000824. That's crazy unlikely. So basically what our p-value is telling us is that our sample slope is unbelievably rare, like super significant, should not be happening. But guess what? It happened, thus giving us evidence that the null is wrong. There is a linear relationship. In fact, there is a negative relationship, and that is exactly where I'm going with my conclusion. So make sure you compare the p-value to your level of significance, which we use 1%. So since my p-value is less than 0.01, we will reject the null hypothesis. There is statistically significant evidence that a negative slope exists between the weight of a car and its gas mileage. There is a linear relationship which shows that the more a car weighs, the lower its gas mileage in miles per gallon. So I'm giving a nice conclusion in context. I'm saying that I'm going to reject the null. There is evidence that there is a negative slope between these two variables, car weight and gas mileage. And what that negative relationship means is that the more a car weighs, the lower the gas mileage will be. So yes, I saw this negative relationship in my 12 cars, but what we're concluding is that if you were to look at all cars, yes, you would see a negative relationship. All right, let's look at example 2 real quick here. So researchers performed a study where they examined data from a random sample of 16 babies from the United States. Same example we saw in the previous video that we were setting this up. So we looked at the average daily temperature in the city that the baby lived and the number of days it took that baby to learn to walk. Now we do see a slight, not extremely strong, but a slight negative relationship showing that as the average daily temperature in a city goes up, the time it takes for a baby to learn to walk does go down. All right, so here's all the other information that we need, all looking beautiful. And now we're asking the question. Now here's the most important thing we need, right? And that is, of course, the computer output table, because that's going to give us, as you're finding out here, literally everything we need. All right, so the question is, does this data provide significant evidence that there is a negative relationship between the average daily temperature of where a baby lives and the age when the baby begins to walk? So is there a negative relationship? We kind of see one in our data that might confirm that this is somewhat true, but the big question is, if we were to look at all babies living in all cities across the United States, would this be a negative relationship? All right, we're going to conduct a test at the 5% level. So quick review of what we did last video. We have a t-test for the slope between the variables of average daily temperature in a city where a baby lives and the number of days it takes for a baby to begin to walk. The null is that, no, come on, there's no relationship whatsoever. That would be 0. As the temperature goes up, time it takes the baby to walk doesn't change at all because there's no relationship between these variables. And the alternative is what we're trying to show. We're trying to show, no, there really is a negative relationship. As the temperature goes up, time it takes the baby to walk goes down. All right. The second thing, or step 2, is the conditions, of course. You can run through them, but you do need all those extra charts to really check all of them. I mean, the first one, you just need a scatter plot to show a rough negative pattern. 2 and 3 are pretty easy to check based on sample size. It's got to be random and under 10% of the population. But again, we do need that histogram of the residuals to actually confirm that the residuals are approximately normal with no major skewness or outliers. You know, go back. It doesn't look beautiful at all. It doesn't look mound-shaped exactly, but I don't see any major outliers or skewness. So I am okay to go on. And then again, we do need that residual plot to check that 5th and final condition that says that, listen, you know, there's similar variability for each X value. They're not all going all over the place, right? There's some positive, some negative, but I don't have any that are like really big outliers. All right, so now I got to build that sampling distribution, right? I'm essentially saying, hey, I want a model to show me all slopes. And right in the center is the null. 0, no relationship whatsoever. And I do understand that through sampling, you are naturally going to get some samples that are a little higher slope, positive, and you're naturally going to get some slopes that are negative, right? If you're a little bit negative, that doesn't mean anything. If you're a little bit positive, that doesn't mean anything. And that could still confirm that there is no relationship. But if we get too far from that 0 in the center, then maybe we do have evidence. And that is where we need our t-score. So once again, I'm going to share the work for the t-score, but I will show you in a second how it is in that table. So we're going to take our slope that we found, negative 0.5055, and we're going to subtract 0. That is, you know, why am I subtracting 0? Because that's the null hypothesis slope, the slope that's saying, hey, there's no relationship whatsoever. And we're going to divide by our standard error. So we're basically saying, hey, where on that sampling distribution does our sample sit? And it doesn't sit very low at all. Negative 0.6126. So if I'm using that sampling distribution I built, it sits like right here. So it's just a little bit lower. It's really not that low at all. All right, but again, check this out, check this out, check this out. Right next to that standard error, just again following the slope. So here's the slope in our sample. That's the slope we saw, negative 0.5055. So in our data, it does show that if you have an increase of 1 degree over from one city to another city, 1 degree in average daily temperature, babies in that city are going to learn to walk about a half a day sooner, okay? And we have the standard error right here, which we needed for that t-score, but we actually have the t-score right in front of us, negative 0.6126. Now, don't be mad if your t-score doesn't match up perfectly with the one in the chart. They're not doing any rounding, so that could be why, but we were pretty close. All right, and then we need that p-value. So remember, a p-value is the probability that any other sample slope is more extreme, which in that case would be lower than ours. Why lower? Because we want to look negative, and our slope is negative, so more extreme would be even more negative. And to answer that question, we're going to find a t-score less than my t-score. So these two questions are these two statements are exactly the same. One just based on slope, one based on the t-score. And then to do that, we are going to use TCDF. So I'll jump to TCDF real quick for you guys. So second vars. Number 6 is our TCDF. So we're going to start at negative 99. We're going to go up to our z-score of negative 0.6126. And 16 babies minus 2 is 14 degrees of freedom. And that's how I got 0.2749 or 0.2750, depending how you round. Actually, I see I wrote 0.2769. It could just be a typo by me there. But again, in the right neighborhood. Sorry about that. All right, now, go back to that computer regression analysis. Check out what they got here, 0.5507. Remember, as I explained earlier, that's the p-value if your alternative is not equal to. Because when the numbers are crunched for this entire table, they don't know that you even have a null and an alternative hypothesis. They don't even care. So the p-value is based on an alternative of not equal to. Because they don't know. They don't know if you want to go positive or negative. They just say, hey, here's the p-value for it to be something different. So if you take our p-value and double it, you're going to get something pretty close to 0.5507. Or if you do want to use the p-value 0.5507, you do have to cut it in half because this is a single-sided test. We only are looking for evidence of a negative relationship. All right, so now we're going to go on to our conclusion. So since my p-value of 0.27 is greater than 0.05, that's the significance level we were told to use, I'm going to fail to reject the null. This is not an unlikely sample. The probability of seeing our data, if the null is true, so if there is no relationship, the probability of seeing our sample is very likely, thus giving me evidence that there is probably no relationship here. So there is no statistically significant evidence that there exists a negative linear relationship between the average daily temperature of the city a baby lives in and the number of days until that baby walks. Listen, yes, we did see a relationship. We did see a slight negative. We did calculate the slope. We did get a negative slope for our data. But you know what? The relationship we are seeing is probably just due to chance. We probably saw a negative relationship because, listen, anytime you throw a bunch of dots into a scatter plot, you're going to see roughly something, but it doesn't necessarily mean that it's meaningful or that it's true for the entire population. So yes, we saw a negative relationship in our 16 babies, but if we were to look at all babies, we probably would not see much of a relationship whatsoever. So there's simply no evidence to support that there is, in fact, a negative linear relationship between these two variables. All right, one more example I want to take a look at here with you guys. Just, the point of I want to look at this example is just to show you how you really could answer everything you have just from looking at the computer output table. So, windmills generate electricity by transferring energy from wind to turbine. A study was conducted to examine the relationship between wind velocity in miles per hour and electricity production in amps. For the windmill, measurements were taken on 25 randomly selected days, and the computer output for the regression analysis for predicting electricity production based on wind velocity is given below. The regression model assumptions were checked. Oh, that is awesome, right? The regression model assumptions were checked. That's the conditions, right? The conditions are the assumptions. So all of the conditions are checked. We don't even have to worry about those conditions, right? I told you a lot of times in the AP they do that. All right, so and determined to be reasonable. Oh, it says and checked and determined to be reasonable over the interval of wind speeds represented for the data. There were, which were 10 miles per hour to 40 miles per hour. So our data ranged from about 10 miles per hour to 40 miles per hour. So essentially what we're looking at here, guys, is two variables. Wind speed in a windmill and electricity produced from that windmill. And I don't know, I don't really know a whole lot about windmills. I'm a math teacher, but I'm pretty sure that if the wind's blowing faster, the windmill's going to spin faster and more energy will be created. So it does seem that there's going to be a positive relationship. In fact, if we looked at our sample of 25 measurements, we see a positive slope. we see a slope of 0.24. So that tells me for every 1 mile per hour that the wind increased, we get 0.24 more amps of electricity produced. Okay, great. So the question could be, is there statistically convincing evidence that electricity production by the windmill is related to wind velocity? Is there significant evidence of a relationship between these two variables? Well, let's check this out real quick, right? We're not going to run through the whole test, but the null would be that, oh no, come on, there's no relationship. And the alternative would be, no, there really is a relationship. Now notice the question never said positive or negative. So I'm actually going to use the not equal to line, or not equal to sign. It makes sense that it would be positive, more wind, more electricity, but it never said that. Okay, so I'm going to use the not equal to. Now, step 3 would be actually getting the t-score, but I don't need to get it. It's right there, 12.63. That's a crazy high t-score. And then even the p-value, guess what? Don't need to do any math because look, they're telling you the p-value is essentially 0. So basically they're saying that our slope essentially has a 0% chance of occurring, which is pretty unlikely last time I checked, but it did happen. So we would definitely reject the null. There is statistically significant evidence. In fact, there's a ton of it with such a low p-value. There is statistically significant evidence that electricity production by the windmill is related to wind velocity. There is clearly a relationship between these two variables, wind velocity and electricity production. And that's very evident without me having to do a whole lot of math. Now, if I have to write this up, obviously I'm going to write it up all nice. I don't have to, I could skip step 2 because I already have the conditions checked. But again, the t-score is given, the p-value is given. All I'm going to basically say at the end here is, hey, since my p-value is of 0.000, and remember, the p-value in the table is the correct p-value on an alternative of not equal to. So if the p-value is less than, well, 0 is going to be less than 1% or 5%. So I will clearly reject the null. There is significant evidence that electricity production by windmill is related to wind velocity. So I think it's pretty cool that, yeah, we understand all these numbers, I hope by now. But if you just look at this chart, you don't really need a whole lot else to say, yeah, look at that p-value. There's clearly a relationship between these two variables. All right, guys, that's it. Awesome video. Hope it helps. Pretty good unit. Hope it all made sense.